So, dear students, we are beginning the second lecture of the course time series analysis. Today's topic: specification selection and parameter estimation for autoregressive, moving average, and ARMA models. Let's start by estimating the parameters of the autoregressive model. It is simpler and clearer because the least squares methods for estimating the parameters of this model works very well. We apply the least squares method. That is, we need to minimize the sum of the deviations of the actual values from the model. The cap here is a model estimate corresponding to some autoregressive process with given parameter. And this is the original empirical observable data. We apply the standard least squares method. N is the total number of available observations. P is the order of the autoregressive model. Here it is the equation of the autoregressive model itself. And minimize this functional, we must take partial derivatives for each autoregressive coefficient and equate these partial derivatives to the zero. Further, by solving this equation for each autoregression coefficient, we get the following system of equation. It turns out that we have P equations corresponding to the order of the autoregressive model, and it is clear that this system of equations for finding the parameters of the autoregressive model through the least squares determines the coefficients A1, A2, A3, and so on, AP, depending on autocorrelation coefficients. That is, in fact, this system of equations show that the coefficients of the autoregressive model are completely dependent on the autocorrelation coefficients. Well, this is its main feature. As a matter of fact, these autoregression coefficients pull over the main content of the autocorrelation coefficients of the analyzed time series, and therefore the residuals of the autoregressive model are not autocorrelated. That is, if you build the model correctly, then its essence is that the residuals become independent random variables, pure white noise. The autoregressive model constant, A0, is determined by the formula through the average value of the original series Y. We already went through this in the previous lecture when we considered how the math expectations of the value Y is calculated. These are autoregression coefficients determined from this equation. And this is the error variance. It is considered as a sample variance due to model error. So model error is our original observed values minus the model itself. Epsilon t squared is our squared model error. When we use the least squares method to estimate the higher parameters, an important requirement is that we still have residuals of the epsilon t that do not have autocorrelation. This is an important theoretical requirement It is not very important for forecasting, but it is necessary to maintain the theoretical purity of the model. Therefore, we check the residuals of the model for autocorrelation using the Liouville box test. While the number of degrees of freedom we must reduce by the number of parameters of autoregressive model. Theoretically, it is recommended that if you nevertheless build an autoregressive model and found some autocorrelation in its residuals, then this order P should be increased. But this rule can be avoided if you are interested in the simplest model and if you are interested in, by and large, tolerable forecasting, more or less correct forecasting. That is, in this case, for these purposes, sometimes you can remain the residuals of the model autocorrelated, because once again, an increase in parameters of autoregressive models do reduce autocorrelation, but in practice, as you will see from your experience at seminars, it practically does not modify your final forecasts in any significant way. The unbiasedness and consistency of our estimates is guaranteed by the lack of autocorrelation of residuals. But looking ahead, another effect is the square of the residuals of the model, i.e. epsilon squared, has autocorrelation. This is the so-called arch effect. And this arch effect opens up prospects for constructing conditional heteroscedasticity models, the arch model and the Garch model. We will be aware of this a little further. So now the square of the residuals of the model which has autocorrelation should not confuse us. In addition to the least squares method, the maximization of the likelihood function can also be used to estimate the parameters of the autoregressive model. The likelihood function for the autoregression model is the probability of simultaneous occurrence of observed events y1, y2, y3, and yn, provided that these events occurred as a result of the data generation process in accordance with the YT model with a cap. And this probability, by definition, we consider it as the probability of falling out of the initial values y1, y2, yp, these initial values for which we still cannot build an autoregressive model because we have no prehistory, and then multiply this probability by the probability of falling out yp plus 1, provided that the previous values are known and provided that they correspond to the capped YT model. So here P is the order of the autoregression model. N is our final sample. And there is a probability is already considered, provided that the previous values are known and the model exists. This probability we need to maximize by sorting through the parameters of the autoregression model. these conditional probabilities, the second part is usually considered as the normal distribution with some mean and variance. And then we have these conditional probabilities have such distribution function, a distribution density function. Here yt is observed value. So this is a model value, and this is our variance. In conditional likelihood function, these first initial probabilities are taken equal to 1 because we cannot say anything about them, because there is no prehistory and we cannot build a model. And in this case, the logarithm of likelihood function is taken. The property of logarithm is very convenient to get rid of these products and turn them into sums. Therefore, the logarithm of the likelihood function is often used. This means that we have the logarithm of the likelihood function turns into such a value. That is, here it is, n minus p divided by 2 is the result of summation. N minus t is the result of summation. This first factor here, it turns into the first term. But this second factor of the exponent in the power, after taking logarithm, it turns into this second term. Now we maximize this function by iterating over their parameter estimate. In fact, here the estimation of the parameters is only in the numerator of the second term. Sigma, since it is supposed to be equal to a constant, it also does not affect anything. And accordingly, with such a conclusion, the conditional likelihood estimates are identical to the least squares estimates. The conditional likelihood function is needed for more advanced time series analysis, such as nonlinear model or conditional heteroscedasticity models. Therefore, here we must introduce it so that you really understand the general direction of constructing this function, and later in more complex time series model we will already say that the least squares method does not work, only the conditional or exact likelihood function works here. The exact likelihood function imposes additional conditions on the distribution of initial probabilities, according to which we do not yet have a history and cannot estimate the model parameters. For example, they are assumed to be normally distributed with some standard deviation and some mean. And now, depending on these assumptions, the estimates may already differ from the method of least squares. It follows from this equation that as the number of observations tends to infinity, the exact and conditional likelihood estimates converge. This is the so-called asymptotic equivalence. Therefore, this terminology must be understood: how the likelihood function is constructed, how the conditional likelihood is estimated, how the exact likelihood function is estimated. For the autoregression model, we don't really need these functions because they give us the same result as the least squares. But in the future, they will be very useful to us. After we talked about estimating the parameters of the autoregressive model, the question of choosing the order P of the autoregressive model remains unanswered. That is, which autoregressive model should we train on existing data? Autoregressive model 1, autoregressive model 2, or autoregressive model 7? This remains unclear. What are the approaches here? The first option is when we iterate through the specifications of the model one by one, each time increasing the order of P, and as a result choose the specification in which there is no autocorrelation in residuals at a given significant level. Autocorrelation in the residuals is checked using the Leunbox test. That is, we sort through the models one by one. First IR1, we check the autocorrelation of its residuals. If there is no autocorrelation in the residuals, then we take IR1. By the way, I missed it, but in fact the simplest model is IR0. So generally speaking, pure formally, we should start with IR0. Firstly IR0, then trying IR1, IR2, and so on. But this is a bit long and routine, so option 2 exists. It consists the fact that for selecting the order of autoregression model, you can use the partial autocorrelation function, PACF. This function is built as follows. The autoregression models are sorted one by one. The first, the second, the third. It is not necessary to sort out the 0 one. And these coefficients are estimated at corresponding yt minus e. That is, the first model is the coefficient at yt minus e. If the second model is the coefficient at yt minus 2, that is A11 for the first model, A22 for the second model, and A33, and so on, AKK for the last model. These are the coefficients that make up the partial autocorrelation function. Or they say in another way, the significance of these coefficients in the PAC function. Next, this PAC function consisting of these coefficients, the diagonal coefficients of the autoregressive model, is already been checked for significance. It is known that where our coefficient becomes significant, that is, it is already greater than the optimal autoregression parameter, then the distribution of the root of n to these autoregression coefficients has a normal distribution with parameters 0 and 1. That is, using this property, in fact, a partial correlation function allows us to test that the null hypothesis H0 is that the optimal order P of the process IRP corresponds to a certain order K. K we sort through 1, 2, 3, 4, 5, and so on against H1 alternative hypothesis that the optimal parameter is larger, i.e. P equals to K plus 1. not current, but the next. And if this statistic is the root of n multiplied by the coefficient akk is greater than 1, then H0 reject. If it turns out to be less than the normal distribution with coefficients 0 and 1, then H0 hypothesis is accepted. That is, in other words, we simply build this PAC function in the statistical package and determine the parameter P based on the significance of the PAC coefficient. That is, as soon as the PAC parameter becomes insignificant, we immediately cut off the following autoregression legs, not using them and not including them in the model. Also, since our IRP is quite normally estimated by the least squares method, we can use R squared or R squared adjusted to assess the descriptive ability of the model. But choosing the order of the model based on this criteria is not recommended. Just as it is not recommended to choose the order of the model based on the t-statistic, that is, if you immediately included in the IR3 model and just looked at the significance of the coefficients of the test statistic, then you may experience overfitting. All of these coefficients can be significant, but in fact, PACF is a more accurate measure for choosing the order of a model, if you often points you to IR2 or IR1. That is the main summary. The order of autoregressive model is recommended to be estimated based on the PACF function. Let's consider the first example. You have a DGA.txt file in your handouts. There is a price level in the United States. Based on this price level, you can calculate the first differences. This will be monthly inflation. The file represents the logarithm of the price level, so the first differences are monthly inflation in terms of log returns. Here it is necessary to predict this monthly inflation. For this, it is necessary to build an IRP model. So the first step, we calculate PACF. That is, we run the function. It is in the handouts. There is a file IR model example R. This file contains all the syntax of used function. So let's calculate this partial autocorrelation function. Here it gives us such a result. This is the value of the partial autocorrelation functions at the level of 5% significance. And this is PACF with corresponding order. That is, this is what was K on the previous slide, which we sort through. And we accordingly cut off those K that are significant. That is, the first 4 parameters are exactly significant, respectively, which means that IR4 is definitely needed in this case. That is, at least IR4 we are building. IR5 is already in question. The insignificance is visible here. IR6 can also be put here they are questions about significance, but a little significance is. IR8, IR9 are slightly significant. IR11, that is here on the verge of this significance, we have some alternatives. This is a very important choice of the researcher, what we need. IR4 for sure, IR6 questionable, IR9, IR11. Here for alternatives. We also can include IR20 in the model if for some reason it is necessary. But this inclusion of additional legs in the model is necessary only for theoretical purity of the model, in order to completely eliminate autocorrelation in the residuals. But these huge legs will give practically nothing as an increase in the accuracy of forecasting. That is, there will be such a microscopic improvement in the accuracy of the forecast that it is quite possible to ignore these distant lags and not include them in the model. That is, I would say that from the standpoint of forecasting accuracy, the first 4 legs will be influenced, and everything else will be such a small influence that it can be neglected in practice. Although theoretically, of course, all this should be included in the model. The next step is to estimate the parameters of the IR4 model. This is our base model, which we defined on the previous slide using PACF. Here we call the LM function using R. And here we have a formula for the first CPI difference, that is our inflation. There is a function of 4 regressors. Inflation with the first leg, inflation with the second, inflation with the third, inflation with the fourth. Here I'm using the LM function for now, while on the next slide we will look at the ARMA function, because both can be used for estimating IR parameters. But you should understand both of these alternatives. Of course, the ARMA function is more widely used for further testing when you are more experienced with predictive models. In future, you will, of course, not use LM, but ARMA function. Here, there is given a distribution of residuals of this model, and here they are coefficients. Intercept is our parameter A0 of the autoregressive model. Estimates, standard errors, the statistics, and significance. Regression coefficients at the first lag, at the second lag, and third lag, that is A1, A2, A3, and A4. Here there are significance of the autoregression coefficients, which means that they all turn to be significant. R squared and R squared adjusted. This is what we see in the IR4 model. Accordingly, here you can see the IR6 model, which is an alternative. and we must also understand it, compare it with AR4 model. Here two legs added to this LM formula, L5 and L6 as a regressor. L5 is not significant at the 10% level. L6 is significant 5% level. That is, you can add regressors and observe the improvement of R-squared adjusted. But still, in autoregressive models, this is not the main criteria for making a decision. That is, based on R-squared adjusted, one cannot say that IR6 model is better than IR4 model. The main criteria is the autocorrelation of residuals. That is, once again, the meaning of using autoregressive moving average and ARMA model is not only forecasting it. First of all, it is the correct inclusion of time series autocorrelation in the model. And if we include this autocorrelation correctly, then the residuals should not have autocorrelation. Therefore, we must check the residuals of our autocorrelation function in conclusion. To do this, we build an autocorrelation function, ACF. This is not PACF, it's not a partial autocorrelation function, it's just ACF, autocorrelation function. It's just a regular legged autocorrelation coefficients. And we see the autocorrelation coefficients as significant. It is clear that there are some outliers, especially on 20th leg, which we have shown on the previous PACF slide that it is significant and we did not include it in the model. Therefore, it is natural that we did not include it in model, and here in the residual it was translated. This autocorrelation is on 20th leg. But more precisely, we run the Leung box test. In the handouts, there is a command to call this test, and we see the degrees of freedom. There you need to put the number of degrees of freedom. The number of legs is recommended to correspond to the logarithm of the available sample number, and the number of degrees of freedom for which we check should correspond to the parameter P. That is the number of parameters of the autoregressive model. That is 4. That is the number of degrees of freedom. The value of parameter M will now be equal to 7 minus 4 equals to 3. And this model gives us a p-value of 0.25. 20 and 5. That is, it is our probability to make an error recognizing that the values do not have autocorrelation. That is, it means that we cannot reject the null hypothesis of the absence of autocorrelation. That is, in fact, here the IR4 model turns out to be suitable with p-value of 0.2. That is, at 10% significance level, we have suggesting that it has no correlation. It has no autocorrelation. And the IR6 model, we check it in the same way. We see that with the help of Leung box test, the value of approximately the same. The p-value is approximately the same. 0.2047. That is, we also do not have autocorrelation for this model. About these degrees of freedom, once again, it means that these degrees of freedom 3 corresponds to the natural logarithm of the number of data, where about 7 it turns out minus the number of the model parameters, i.e. 4, that is the result is 3. But this one is obtained as the natural logarithm of the number of data, that is 7, minus the number of the model parameters, that is 6. In the event that you build too many parameters, this degree of freedom can go down for you. Well, in fact, this limitation of logarithm of the number of observation is in fact an empirical limit on the maximum number of coefficients that you can include in your autoregression model. That is, it is not recommended to increase the number of parameters of the autoregressive model too much when you have a small sample. In this case, both models IR4 and IR6 are suitable, but since IR6 has no visible advantages over IR4 model, we prefer economy, that is the IR4 model. Here is the conclusion. The final specification of the IRP model for monthly inflation is the IR4 model. Here there are the coefficients of our autoregressive model. This is the coefficient A0. This is the standard deviation of the residuals. What else is important? If you use the ARMA function to evaluate the autoregressive parameters, I used LM in the previous slide. And if you used the ARMA function, you will have its syntax in the IR example file and take the syntax from there and repeat the calculation. That application of this ARMA function will give you the same autoregression coefficients, but there is a difference in the drift parameter, or significant difference in the drift parameter or A0 coefficient from LM function. And it's different for above 2 times. That is, the previous coefficients are correct, but this drift is very different between LM and ARMA model. You need to carefully read the help for the ARMA function in R, and then you will see that in the ARMA function under the drift coefficient or intercept, depending on which query you enter, a selective math expectation for the analyzed time series is presented. And when you have a sample expectation for the analyzed series, you can calculate the coefficient A0 from the formula for the average for IRP process. We recall the previous lecture, or recall what was written on the first slide today, and the coefficient A0 is calculated from this equation. That is, in order to turn this 0.24 into something like 0.12, you must calculate A0 using this formula. Then A0 will turn out to be close to this value. This is a small important feature of this function, so please pay attention to it. That is, the drift parameter in the ARMA function is not A0 from the autoregressive process. We are starting to study these models deeper and deeper, and now consider the following example. We have data on the logarithm of annual GDP per capita for United States at constant prices. This is data from about starting of the 19th century. So this is data for Great Depression of 29th, 34th years of 20th century, the decline in GDP, then Roosevelt's economic policy, and this is post-war years, and then the history of the history after the Second World War, and this is the small crisis of 2008. And we need to predict this logarithm of annual GDP per capita in the United States at constant prices. That is, we run PACF and see the following feature. PACF with order 1 is close to unity. That is, it is clear that only the first leg is significant and there are no other alternatives. Here is that we conclude based on PACF. We need to construct an autoregressive model with order 1. We estimate the parameters of the IR1 model. It turns out that the coefficient at first lag is nearly 1. The intercept is A1, since we used LM function, is minus 0.5 thousandths. And now we check the autocorrelation of the residuals and see a significant first leg, a significant fourth leg, and significant fifth leg. And the lunch of Green box test indicates that the residuals are strongly autocorrelated. That is, the probability of making an error by rejecting the hypothesis of the absence of autocorrelation is 0. Through PAC, we see that we have no alternative. But here it is obvious that if we increase the order of the model, then somehow it is not clear. PAC probably doesn't work. But there is a small subplating here, which is connected with this fact. The autoregressive model has one particular feature that must be theoretically considered. It is called a unit root in an autoregressive model. And the fact that a unit root has turned out here is evidenced by this coefficient close to 1. It can be 0.999, maybe a little higher than 1. That is, coefficient close to 1 in a regressor with a lag of 1. Let's look at this unit root problem theoretically. Let we have some process IRP. We represent it as a polynomial from the shift operator, transfer all these coefficients to the left side, take it out of brackets, and use the shift operator. Having solved the resulting characteristic equation, we expand these polynomials into the factors. And let one of the roots, Z1, Z2, Zp, of the characteristic equation be equal to 1. So my question, what will happen then? So the answer is that then we have that sum of the factors turn into 1 minus L, and the remaining factor form a polynomial with a p minus 1 order, denoted as A star with L. Here is what we got. If we multiply 1 minus L by y. Then we get a polynomial of a degree p minus 1 multiply on yt minus 1 equals to epsilon. Here we have delta y, or the first difference. That is yt minus 1 is delta y, first difference. And now if we apply this first difference, multiply it by this polynomial, transfer the result of the polynomial to the right side, then we've got that our process IRP having a unit root where one of the roots of the characteristic equation is equal to 1, that is in fact the same as the process of autoregression of order p minus 1, or the first difference is delta y, that is the sum from 1 to p minus 1, multiply the new coefficients with asterisks, multiply by delta y with a leg, not by y itself, but by delta y, the first difference, and plus the epsilon that has already been. That is, this is the result if autoregressive process for yt has a unit root, then it turns out that the process itself is formed as yt is equal to yt minus 1 plus delta y. Here, two autoregression from the first differences. That is, this decrease in the order of the process is empirically very important. Here we theoretically showed that this is a decrease in the order of the process. That is, if there is a unit root, this process turns out into the process of order p minus 1, but on the first differences. So the same is true for ARMA PK model. Let's look at an example to understand it's clearer. Here we have some ARMA 2-1 process, which is described by this equation. Consider whether there is a unit root in this process or not. We'll transfer the autoregression parameters to the left side and represent this record as a polynomial of the shift operator. Here we have it converted. Yt is putting out of brackets. Here will be 1 minus 0.2 multiply L and multiply 1 minus L multiply Yt. And in the right side, we put out the brackets epsilon t, and in the brackets we have 1 minus 0.5 multiply L. And now we see that the characteristic equation for autoregression has a unit root. It is shown here because here we will have a unit. And accordingly, this unit root allows us to move on to the first differences. That is, this is the product of the second factor by Yt. We open it as Yt minus 1. And here we have the first difference. And now when we already reveal the first differences and leave dyt itself on the left side and transfer dyt minus 1 to the right side, it respectively multiply by 0.2 and the sign then changes on the right side during the transfer. Then we've got the process ARMA 1,1, but on the first differences. That is, this means that this is initial equation of the ARMA 2,1 process. It exactly corresponds to this equation, but on the first differences. Theoretically, this is the same ARMA 2,1 on YT and ARMA 1,1 on the first differences. But empirically, the question is, how do you estimate the parameters from real data? On the original series or on the first differences? The empirical error due to the estimation of the parameters on an indicator with a unit root becomes very large. Therefore, it is very important to test this unit root, and the equation of ARMA parameters estimation taking into account the unit root should already occur either on the initial series or on the first differences, if the unit root is present. After this theory and understanding the question arises of how to test the unit root on empirical data. And in this case, when testing this unit root, one speaks of the hypothesis that the exponent yt is non-stationary. These two concepts are now closely related with the unit root of the IR model, and yt is a non-stationary indicator. For testing non-stationarity, the most well-known test is the Dickey-Fuller test, DF test. How is it built? We have the first-order autoregressive model. Yt is A1 multiplied Yt minus 1 plus A0 plus residual. Parameters A1 and A0 are estimated using the least squares method. Testing a unit root means testing the hypothesis that this coefficient A1 is equal to 1. And this can be verified using standard test statistics. Dickey-Fuller showed that under the null hypothesis, A1 equals to 1, this t-statistics does not have a t-distribution even asymptotically. The correct and critical values for these statistics are completely different. They are presented in our table below. So T big is our sample size. These are critical values at 1 and 5% levels. There are 3 versions of this test, but I will say this a little later. The basic version of this test is a test with a constant and without trend. That is, if you just apply the Dickey-Fuller test to some initial data at first, then you always take the main hypothesis with a constant and without trend. Why do we need an alternative? I will tell you a little later. Now, using our theoretical knowledge with the unit root, we will rewrite this autoregressive model in slightly different form. That is, we will replace yt with yt minus 1 plus delta y. And we've got the usual type of model used in this test. That is, the first difference is a1 minus 1 multiply yt minus 1 plus a0 plus epsilon t. Here we have some coefficient. Let's denote it a star, a1 star. And if a1 equal to 1, then a1 star is equal to 0. In fact, regression is tested for the significance of the difference of this coefficient A1 star from 0. Its difference from 0 is equivalent to the fact that A1 is equal to 1. The null hypothesis is being tested is that this A1 is equal 1. This means non-stationarity and the correctnesses of the model on the first differences. In this case, we only get A0 on the first differences. That is, R0 model arises on the first differences. We test it carried out against the alternative hypothesis that A1 is not equal to 1, which means that the YT is stationarity. This means that the original R1 model is correct. When is specification used a constant used, and when is a specification with a trend used? If considering H0 for some reason, we have reason to believe that the original tested model should have a theoretical constraint A0 equals to 0, then we use the version without constant and without of trend. In practice, I have never seen or met such justification anywhere. In some cases, a situation really arises when we have theoretical assumptions about the absence of the constant. But these are such rare situations we are aware of such things will not arise during our course. A version with a constant and with trend, it includes model specification with AT multiply T added, as AT is some trend factor and T is a linear time. Constant and trend testing is widely used to test so-called trend stationary models as an alternative. This fact is that before the advent of these autoregressive models, trend stationary models were widely used in econometrics, and at that moment, in order to compare these specifications, that is the presence of a unit root versus the trend stationary hypothesis, this version of the Dickey-Fuller test with a constant and with a trend was developed. To summarize, when you just see a series without any additional features, you are using a version of the test with a constant and without trend, the main version of this Dickey-Fuller test for our discipline. An extension of the Dickey-Fuller test is the ADF test, Augmented Dickey-Fuller test. It considers as a null hypothesis not only IR1 process, but also the IR2 process, the IR3 process, and in general cases, IRP process. That is, we have a null hypothesis that process Y has a distribution or pattern according to the second order autoregressive model. We represent YT through YT minus 1 and delta Y. We do the same for YT minus 2, YT minus 1 minus delta YT. And accordingly, these coefficients go here. And we have such a specification for testing that the first difference is the lag value of the initial series with such coefficients minus A2 multiply delta YT minus 1 plus A0 plus epsilon. The equality of the coefficients A1 plus AT to 1 is tested. Note A1 plus, not A1 equals to 1 anymore, but the sum of the autoregression coefficients must be equal to 1, so that this is in brackets, in fact, is equal to 0. And here is the same for IR3 model. The same transformation is done, and it turns out that we are testing the equation of the first difference, that is the sum of the coefficients a1, a2, and a3 minus 1 multiplied by the original series with a lag and by regression with the first difference with a lag, the first difference with 2 lag. And the same can be obtained by analogy with these coefficients when testing for the ARP model in general case, tested using standard statistics. The null hypothesis is tested. The sum of autoregression coefficients is equal to 1. That is not stationarity or the presence of the unit root against the alternative hypothesis. The coefficient is not equal to 1, that is stationarity. The critical values are the same as those of Dickey-Fuller test, and there are also these 3 versions. The main one with a constant and without trend. This order of the autoregressive model is important characteristic of the Dickey-Fuller test. When you run this Dickey-Fuller test in R, you will need to specify the number of legs for your autoregressive model there. This is the number of legs for your autoregressive model that you fit according to the product of your YT or DYT variable. That is the initial indicator, or it's the first differences analyzed for stationarity. Accordingly, by setting this number of legs that are tested in the extended Dickey-Fuller test, you already get one or another specification, but which affects the p-value of your hypothesis about the non-stationarity of the time series against the hypothesis of its stationarity. Except the Dickey-Fuller test, there are 2 other econometric tests for stationarity. The first test is called the KPSS test. The second test is the Phillips-Perron test. The PP test repeats the ADF test very much. Test statistics are set a little differently there, but there are studies that shows that the Phillips-Perron test gives a higher probability of error than Dickey-Fuller test. That is, in practice, I see no reason to use this test in addition to the Dickey-Fuller test. But the KPSS test has some original features. And the fact is that the KPSS test is designed in the opposite direction. That is, if our Dickey-Fuller test considers the null hypothesis, the series is not stationary, there is a unit root, then it controls the probability of the first type error, that H0 is incorrectly rejected. But KPSS test was developed in the opposite direction. It was developed on the basis of the theoretical hypothesis that the series is stationary. That is, when we have theoretical grounds to believe that the series is stationary, then we apply the KPSS test. And it accordingly controls the probability of type 1 error, that is the probability that we incorrectly reject R0. The simultaneous application of these 2 tests give rise to uncertainty and discussions, which are often sometimes understood that this uncertainty cannot be revealed in any way. Here the logic is such that if, according to some theoretical assumption, you have reasons to believe that these indicators should be stationary, then you apply the KPSS test. If you do not have such theoretical grounds, you apply the null hypothesis that the series is not stationary. Then you use the ADF test. Everything else in this synthesis, where one method say one thing, another method say another. There is already a matter of some theoretical discussions, scientific discussion, but it should not much concern students. In addition, the students must also remember that any series such as GDP or company's revenue profit, it exists not only for one company, it exists for many similar companies. That is, in other words, these indicators are members of a certain family. And these tests for stationarity should be applied more accurately, not to one member of the family, but to the whole family. And here already there are grounds for justifying stationarity based on a single series, but on the basis of the theoretical assumption under test results for the entire family. For example, testing with the Dickey-Fuller test of GDP per capita is widespread. For most countries, GDP per capita is a non-stationary process, but for some countries, at the 5 or 1 person significance level, GDP per capita is a stationary indicator. How to be here? Could it be that the GDP of France is a stationary process, while the GDP of, say, for example, United States is a non-stationary process? That is, if you are faced with such uncertainty, theory or econometrics tells you that you need to accept the hypothesis of stationary for the whole family. That is, if for most countries GDP per capita is non-stationary, then it is also non-stationary for France, even though the Dickey-Fuller test shows its stationarity. That is, here when applying the stationarity test, you need to take into account such nuances. In econometrics, not everything follows a standard template, standard rule. That is, econometrics itself and these tests themselves, when you use them for justification, they do not come down to just blindly following the rules. You must understand the alternatives, you must understand the subtleties that we are discussing here in the course of the lecture. And in the course of your practical work, you will also come across it. And accordingly, taking into account these subtleties on the basis of competent reasoning, you should already be making informed decisions for which you personally, as a researcher, take responsibility. Go ahead. So far, we have tested the original series for stationarity, and in the case of its non-stationarity, we have received the basis for constructing an autoregressive model on the first differences. However, it may turn out that the first difference will also have a unit root. That is, the first differences in economic indicator also need to be tested for stationarity. In this case, the regression that is being tested looks like this. There is a second difference of initial series, delta 2 yt. This is a regression from the first difference with a lag of 1, and a regression from the second difference with a lag of 2, 3, and so on. This multiplier is being tested, the sum of autoregression coefficients -1 is equal to 0 or not. In the first difference, if the first difference turns out to be non-stationary, then accordingly we similarly pass to the second differences, and so on. For economic data, one does not have to go further than the second difference. That is, again, accordingly to the totality of applying tests to members of the entire family, most economic indicators are either stationary in themselves or stationary in the first differences. It is very rare when an economic indicator is stationary in the second difference. Never when economic indicators are no longer stationary in the third difference, and so on. This necessity of testing the unit root hypothesis on the various differences generates ARMA model. That is, we had an ARMA PK model, and now there is an ARMA PQK model. ARMA means autoregressive integrated moving average model. Integrated is our period, the order of taking the differences, which is denoted by the letter Q. P is the number of parameters of the autoregressive process. K is the pure parameters of the moving average process. And Q is the order in which the difference is taken. Well, as a matter of that fact, this ARMA model is written in this way. If Q equals to 1, then this model is on the initial YT data. And this is the moving average after regressive model is built. If Q equals to 1, then ARMA model is based on the first differences. If Q equals to 2, then ARMA model is built on the second differences. But these are in fact some generalizations. So the R function that allows us to build an ARMA model is actually not called an ARMA function, but an ARMA function. And there we mean that you can specify this order of taking the differences to build a model. Now, having dealt with these tests, with unit roots and with the concept of stationarity, we can see how, in previous example, and estimate the parameters of the autoregressive model for US GDP per capita influence on the result of the model. There, recall, we've got a little nonsense consisting in the fact that our PAC showed only one significant regression parameter, and the autocorrelation in the residuals was still preserved after constructing the model, and we could not do anything about it. The fact is that in that previous algorithm, we missed the starting test. The starting test for time series analysis is that we had to check this series for stationarity. We apply this test. ADF gives us the value for YT, the original series, 0.44. For the first difference, delta Y, ADF gives us minus 9.4. At the same time, the critical value of the ADF test is minus 3.5 at 1% level for a given number of elements in the series. That is, the hypothesis of unit root is not rejected for YT, but is rejected for delta Y minus T. This means that yt is considered as a non-stationary indicator, while delta yt is considered as stationary indicator. Therefore, it means that IRP model we must build on the first differences. It is our main conclusion from this autoregressive process and the stationarity test. Now we calculate PACF for the first difference, delta y. We see that we have the significance on the first leg. We see the significance on the fourth leg. We see the significance on the 9th leg. Well, all these legs can be included in the model, so we further evaluate the two most plausible models, AR1 and AR4. Estimating AR1 using a linear model. Here we get the intercept. Here we have the coefficient A1 equals to 0.22. All coefficients are significant. And in the AR4 model, we have the first coefficient. The first leg is significant. The second leg is not significant. The third leg is not significant. The fourth leg is significant at 5% level. R squared adjusted equal to 0.4 and 0.6 respectively. And to honest, it's very close to 0. It increases slightly as the model order increases, but about the same. Then we should check the autocorrelation of the residuals for both models. Here the autocorrelation of residuals for IR1 model. And we see it's significant on 4th and 5th leg. For IR4 model, the autocorrelation of residuals is less significant. And with the help of link box test, taking into account these additional degrees of freedom, we get a fairly low p-value 0.2, and here is 0.1. That is, we still have autocorrelation in the residuals. That is, in other words, we see that neither the IR1 model nor the IR4 model allows us to get rid of the autocorrelation of residuals. What can we do in this case? Firstly, we can once again note on the previous slide that the second and the third parameters of the IR4 model are not significant. And this means that their presence in the model simply increases the number of degrees of freedom and affects the statistical significance of our test. Therefore, we can build a short specification of IR4 model. We consider only the first difference with the first leg and the first difference with the fourth leg as a regressor. And we simply threw out the second and third legs so as not to spend extra coefficients on them. Here we've got the value of the parameters with the fourth leg, first leg, and the fourth leg. Here both coefficients are significant. We have significance at 1% level, and this significance at 5% level. R squared is 0.69, and the Lung box test immediately increase to a p-value of 0.8. Usually here the p-value for the exact absence of autocorrelation should be greater than 0.1. 0.08 is already something you can work with. That is, in this way, by reducing the number of significant parameters, it is quite possible to increase the reliability of the fact that there is no autocorrelation in the residuals of the model. By analogy, if we want to follow the theoretical purity of our model, we must ensure that the p-value of the autocorrelation of the residuals still increases, so we can add another leg to our model. Let's construct a short specification of the IR5 model. This is the initial indicator on the first difference. This is the function of the first difference with the leg 1, a function of the first difference with the leg 4, and the function with the first difference with the leg 5. So we added it. Here the function of the leg 5, the parameters of the model with leg 5, we have a significant at 10% level. Adjusted R squared increased to 7 and 7%. And here the Link box test gives us p-value 0.32. That is more than critical value of 0.1. Accordingly, here we have already fairly sure that this short specification of the IR5 model does not have autocorrelation in the residuals and is theoretically ideal. So the conclusion for this example. For US GDP per capita, 3 model specifications are valid or acceptable. The first is IR1, the second is the short version of IR4 model, and short means that only the first leg and the fourth leg are included. And the short IR5 model, it includes the first leg, the fourth leg, and the fifth leg. The standard deviation we have here is estimated everywhere. Here they are standard deviations. Here you see again between this model a more specific choice. So what we are interested in, theoretical purity of the model. Then we are completely confident in IR5 model. But the second thing that interests us is the accuracy of the prediction. That's when you get the point of building the model, you will see that in terms of forecasting, the effect of IR5 model is not much higher than the effect of the IR1 model. That is, as a compromise model for building a forecast, the IR1 model alone will go well as some simplified version, which loses a little compared to a more extended model. That is, here there is always a choice. On the one hand, theoretical purity and justification that the residuals are pure white noise, but when there are a lot of extra parameters. On the other hand, this theoretical purity does not provide much benefit in practice compared to a simple IR1 model. Now consider the estimation of the parameters of the moving average model and ARMA model. The problem with estimating the parameters of these models is that the regressors are not explicitly known. That is, in this case, this is not only the previous value of the analyzed indicator as in the autoregressive model, but also noises, including previous noises. These epsilon t are not observable. Therefore, OLS cannot be applied here. To understand the other way to obtain it, let's write the conditional likelihood function for the ARMA K process. We have already seen the logarithm of the maximum likelihood function for the autoregression process. Everything will be the same here, except that here in the numerator, we've got the deviation of the original series from the autoregression model. YT is original series. Here we have the squared autoregression model, and we must maximize the maximum likelihood function with respect to the parameter IE. What we have in the numerator is, in fact, we have the model error. Since we do not have these errors explicitly, the only thing we can do theoretically is to present the ARMA-K process as an autoregressive model with an infinity order. That is, use this invertibility property. Here is a representation of the moving average model in terms of a polynomial of the shift operator. We can do the same for the conditional likelihood function for the ARMA PK model. Here we've got a polynomial for the ARMA model. In the numerator, that is, it actually turns out this error epsilon t expressed through the inverse polynomial of the shift operator for the autoregressive model and the polynomial of the shift operator for the moving average model. Here's something like this. You can set the initial error for exact likelihood function, B0 and sigma. The R program does this transformation through a polynomial of the shift operator automatically and finds the parameters of the moving average model and the ARMA models itself. If you do this in Excel, then in the next lecture I will show you how you can find the parameters of the moving average and ARMA on your own. There, it is not all difficult to use numerical optimization methods. But in the case of using the ARMA and AMA model, again, as in the case of autoregressive model, the question arises how to determine the order of model K for moving average and order of P and K for ARMA model. Here the rule is that the choice of order K for moving average model can be made based on the autocorrelation function ACF, not the partial autocorrelation function, not PACF, but ACF. And this optimal order of the moving average model is determined based on the conditions that the kth autocorrelation coefficient is not equal to 0, provided that all the following correlation coefficients are equal to 0. With an ARMA model, PACF and ACF are not suitable for choosing the order of the PK model, and there are approximate methods of choice here. My favorite is EAKF, extended autocorrelation function, and also it is possible to use AIK or B conformation criteria. I like information criteria less because they often overfit model. Still, I will say again that in these AR, AMA, and ARMA models, the issue of savings usually comes to the core, except when we are trying to get closer to theoretical purity of the model with a complete absence of autocorrelation in the residuals. Here on the slide, there are the main tools for determining the order of the ARMA model. That is, here on the top left, we present how the AIK criteria for the ARMA model is calculated. That is, we have some penalty function minus the logarithm of the likelihood function. Big is almost the same, only here instead of 2, the natural logarithm of the sample size is used. The standard rules for using this criteria are that the smaller the criteria, the better the model. Both criteria usually give negative values, so the smaller these negative values, i.e. the farther they are from 0, the better for the model. There are no objective grounds for using these information criteria. In fact, the use of this criteria is the so-called penalty function in mathematics. That is, it is some kind of compromise between the quality of the model and the savings. Theoretically, it is usually said that big is better to use since there is less chance of overfitting the model. Other studies have shown that AIC usually chooses the model with the best predictions one step ahead. In general, there is no reason to use either one or the other. That is, we look at these and that, and further by expert means, we make our own choice in favor of one or the other. Once again, even if we use AIC and BIC approximately, our criteria for choosing a parameter of the ARMA model may be to minimize the number of parameters provided that the residuals of the model do not have autocorrelation. In addition to AIC and BIC, there is also EAKF, an extended autocorrelation function. This approach is closest to me for the ARMA model. Application of the extended autocorrelation function gives us the following results. That is, the rows here are the parameters of the autoregressive model. That is, in fact, this is the intersection of the second line of the third column. This is correspond to the extended autocorrelation function of the ARMA model 1, 2. And these are the coefficients of extended autocorrelation function. If we carefully study their formula, then in fact they are obtained as a result of the following adjustment. The parameter of the autoregressive model corresponding to this line is subtracted from the original series. That is, an autoregressive model is built and the original series is adjusted for this autoregressive model. Some residuals is obtained, and then they look at whether these residuals have autocorrelation or not. And accordingly, these autocorrelation coefficients with these slugs jumped out here at a given level. Taking into account the significance of these autocorrelation coefficients, we will present the final result for AKF in the form of such table. The cross marks of the model that do not fit, on which the autocorrelation coefficients of the residuals are significant. The asterisks are the same. And the zeros are perfectly valid model. That is, from this representation, it is clear that the ARMA 00 model is suitable. Sorry, the ARMA 11 is suitable. The ARMA 12 is suitable to ARMA 13, ARMA 22, and so on. These models are suitable according to this criteria of insignificance of autocorrelation of residuals after adjusting the data for the higher part of the ARMA model. Accordingly, the logic of applying this EAKF is such that all zeros are valid models, but we select the ARMA model by minimizing the number of parameters. So first of all, we should try ARMA 11. Start the process of checking residuals for autocorrelation on it. If there is no autocorrelation in the residuals, And then we see that the ARMA 1.1 model is ideal in terms of economy and in terms of the absence of autocorrelation in the residuals. If we have autocorrelations in the residuals according to the ARMA 1.1 model, then we move on the next model. If there is no autocorrelation of residuals, then we consider it ideal. Well, and so on. In fact, using this EAKF, we are guided by the criteria that we choose a model with a minimum number of parameters and no autocorrelation in residuals. If we are only interested in forecasting, then I would recommend that you simply use the ARMA model with the minimum number of parameters allowed by EAKF. That is, in this case, ARMA 1.1. In my view, EAKF is a sufficient tool for choosing a model parameter. These are widely used IEC-BIC criteria. They are secondary. That is, you can use, but to be honest, for me, the EAKF approach is more understandable than these arbitrary, widely used information criteria that not having a strict justification. Let's try to build the moving average model for US inflation. That is, at the beginning of our lecture, we considered that the IR4 model is the best suited for the US inflation if we work only in terms of an autoregressive model. Now we build a moving average model with order K. To determine the order of model K, we consider the autocorrelation function. The first action, here we see significant coefficients with the first legs, with the second, fourth, fifth, and so on. That is, the autocorrelation coefficients are significant exactly up to 14th leg. Then on the 70th leg, they are significant, and on the 23rd leg, they are significant. Well, ACF points to moving average 14 exactly, maybe to moving average 17, maybe even further. So here there are two alternatives. But here we pass these two alternatives through the ARMA model. Here I already used the ARMA function, not LM test. So here I have all the moving average 14 coefficients. Here it is the drift coefficient. Once again, drift is our mathematical expectations of y in ARMA model. This is not B0, but due to B0 calculates as expectations of yt for moving average 14, this equation is suitable here. So you see many of our parameters are significant. Some parameters, for example, MA7, are not significant. So we can make sure that the 7th autocorrelation leg is significant, but the 7th coefficient of the model is not significant here. This is precisely the reason why we cannot choose the significance parameters of our autoregressive or moving average model based on test statistic. Now for this model, we check the autocorrelation of the residuals, build an autocorrelation function. We see that these first 14 legs, their autocorrelation is fully included in the model. Well, now more strictly, we check for autocorrelation in the residuals using the Leung box test. We run it and understand that here we have an autocorrelation in general at level 0.20. Those we can assume that there is no autocorrelation in the residuals. But if we had autocorrelated residuals, here in this ARMA14 model, we could try the ARMA17 model or ARMA23 model. But there is no need to increase the number of parameters. The residuals are no longer autocorrelated, so ARMA14 is enough for us. Now consider an example of constructing an ARMA model for the same US inflation series. First, we calculate EICF. That is, we have a command in R, EAKF. There you need to connect the TCA package. You will see it in the applicable file. It is in the IR example model file. And now EAKF shows us that the simplest ARMA model that is suitable for this indicator is ARMA11 model. ARMA21 is also suitable, ARMA12, ARMA22 is also suitable, and so on. That is, zeros means all models that are suitable for our indicator. Crosses models that are not suitable. Then we start with the simplest EAKF model, ARMA11. We evaluate its parameters. Here it is the autoregression coefficient of 0.89. Here is the coefficient of moving average -74. Again, drift is the expectations of y. This is not the A0 parameter. Therefore, we calculate A0 through the formula for the expectations of the ARMA model. And these are the autoregression coefficients of ARMA model. Then we calculate the ICF of the residuals of the model. Here we have the 20th leg, again slipped beyond a significant level. The 23rd leg here is a little significant. Previous legs are all removed after correlation by the ARMA11 model. The Lewin box test gives us p-value 0.24. That is, there is no reason to consider the residuals to be autocorrelated. Thus, the ARMA11 model is a valid model. Therefore, there is no point in using all other possible models, and there is no point in increasing the number of parameters. This does not give either the theoretical purity of the model or an increase in the quality of forecasting. Therefore, ARMA11 is a very good model. So here I don't have a slide with a general summary of inflation patterns, but we need to summarize the results for now. So what did we get? We analyzed the IR, ARMA, and ARMA models for US inflation. In the case of IR, we've got the best IR4 model. In the case of ARMA, we've got the best ARMA14 model. In the case of ARMA, we've got the ARMA11 model. Here in this example, the following feature is visible. All these three models gives the same effect, but the number of parameters is saved depending on the different representation. That is, this final ARMA11 model turned out to be a model that achieves the same results primarily by the absence of autocorrelation in the residuals, but only 2 parameters of the model are used versus 4 parameters in the case of an autoregressive model and against 14 parameters in case of moving average model. That is, here ARMA11 turns out to be the best model in the end. But in practice, when we do not have time for more detailed model specification, the autoregressive model is very widely used. That is, when we consider forecasting issues in the next lecture, we will see that between these three options, forecasted by IR, by ARMA, and by ARMA, with the exceptions of saving parameters and the absence of autocorrelation of residuals, the influence of these models on forecasting diversity is practically insignificant. That is, these three versions of the model give, in fact, the same predictions, and the key thing, except for autocorrelation in the residuals, is simply to save model parameter. So once again, in this case, this compromise ARMA 1.1 model is better because it's just two parameters of the model. We are slowly coming to an end. However, there is one more theoretical effect that we must consider. This is the so-called problem of the common roots of the ARMA model. Why does ICF offers us many options for ARMA models? ARMA 1.1, ARMA 2.2, ARMA 1.2, ARMA 2.1, all are valid models according to ICF. The problem lies in these common roots. Let's look at such an example. Let some time series be described by the following ARMA 2.1 model. Y current is Y previous multiplied by factor of 1 plus minus 0.25 multiplies YT minus 2 minus 0.5 multiplies epsilon t minus 1 plus epsilon t. This is our ARMA 2.1 model. Using the shift operator, this model can be rewritten. We transfer y to the left side, apply the shift operator, and we've got such a polynomial for the autoregressive model. Here we have a polynomial for the moving average model. The solution of this characteristic equation for autoregression gives us such a solution that there are two roots of 0.5. Accordingly, we have the same thing on the left side and the right side. That is, these roots in the autoregressive model in the moving average part of this model are common. It does not matter which roots is on the left side. They are the same in this example. At least one must match the one on the right side. Accordingly, you can simultaneously divide the left and the right parts by the same amount. That gives us reduced form. This multiplier here is the reduced with this multiplier. This shows that this is turning into an IR process, since the proposed ARMA model has a common root which allows this model to be simplified and reduced simply to the IR1 model. That is, this is property. It means that the use of the ARMA model in comparison with autoregression or ARMA of the higher order in accordance with ARMA of lower order will often give just overfitting. That is, it is easy to add many extra parameters to the ARMA model, which actually give common roots. That is, we have these common roots due to the sampling error. They can very, very easily grow, and there will not be a strict reduction of the roots, as for example here 0.5 and 0.5. And taking into account the sample, these can be roots of 0.49 and 0.495 thousandths. does these roots are common or not. On the sample data, we look at what seems to be different roots, but when we try to take into account the sampling error, we understand that it is highly likely that these differences in the roots of 0.49 and 0.495 can be caused by sampling error and the fact that we set a specification of the ARMA model with a sufficiently large number of parameters. That is, the simplest version of ARMA give a suitable forecasting quality primarily due to the presence of common roots that arises when estimating parameters in a model of higher order. That is, I emphasize once again that an increase in the ARMA parameters is necessary only for the theoretical purity of the model, in order to completely eliminate the autocorrelation in the residuals. Therefore, there is no need to rush with ARMA overfitting. Include common roots there. No need to prove that the best model is ARMA 445 or ARMA 99. Most likely, when you get such results, you are simply overfit the model. That is, in fact, data generation process is described by ARMA with a lower order than what you find. And what you have identified is simply exploiting the effect of the common roots of the ARMA model. Here is the brief summary of the lecture. The things that we have studied today, what you should already clearly master in your heads. First, when estimating the parameters of an autoregressive model, the ordinary least square method is suitable. It is widely used, and the conditional likelihood function gives the same result. But for moving average and ARMA models, the least squares method cannot be applied in its pure form. The likelihood function is maximized with the representation of ARMA and ARMA process in the form of higher infinity process through a polynomial of the shift operator. We also talked about conditional likelihood and exact likelihood, about the fact that these two obtained estimates are asymptotically equivalent. Next, partial autocorrelation function, PACF, is used to determine the order of the IRP model. To determine the order of the moving average model, we use the autocorrelation function, ACF. To determine the order of the ARMA model, I recommend using EACF. AIC and BIC can also be used. It's up to you. That is, once again, in these models, there are alternatives. All possible valid alternatives should be tested, and the alternative with the least number of the parameters and non-autocorrelated residuals should be chosen. Further, we check the residuals for autocorrelation using the Ljungbox test. If there is autocorrelation, the number of parameters of the model can be increased. Also, the autoregression moving average and ARMA models apply only to stationary time series, where the unit root hypothesis is rejected. This is also an important consequence for us. That is, if we apply these models to non-stationary time series, we will begin to get strange results. Autocorrelation in the residuals will not be reduced. There will be a conflict with PACF, with EAKF. That is, these are important consequences, that I mean that should give a result that these models can be applied only to stationary time series. The series is checked for stationarity using the ADF test. PSS test and Phillips-Perron test are additional tests. You do not need to confirm something with a PSS test or additional research. That is, at the moment here in our first seminar, you should use only the ADF test with a constant and without trend. Everything else is up to your experience. You will understand in which direction which test can be used and for what specific task. We also got acquainted with the ARMA PQK model. This is an extension of the ARMA PK model to the case of non-stationarity of the original series and its Q differences. Q is the order of differencing, and everywhere in the package you will immediately be offered to use the ARMA model, but not ARMA. So when you define the parameter Q, you define Q based on assumption about the stationarity or non-stationarity of the original series. That is, if you have a stationary series in first differences and you build an ARMA model on first differences, you set Q as 1. If your original series is stationary, you set Q to 0. And here is the last conclusion, that the common roots of the ARMA model make it easy to increase the number of parameters without increasing the explanatory power of the model, and we do not need this. Therefore, be careful not to increase the number of parameters of this model once again, and be very careful when using AIC and BIC. They often overfit your model. In conclusion, I give you the final model specification selection algorithm, according to which you should already go and analyze your task at the first seminar. At the step 1, you adjust the series for inflation, if necessary. I emphasize again that inflation adjustment gives significant results when there are changes in inflation. That is, if during the analyzed historical period there were some significant trends in the growing or fall of inflation, then we must take into account inflation. We also logarithm it if necessary. I recommend taking logarithms for most indicators, with the exception of those indicators that can theoretically take negative values. And also we eliminate seasonality with obvious dependence on quarters or month or days of the week. After that, we work with the indicator that is cleared of inflation of seasonality. If necessary, it is taken as a logarithm, and we are already building an ARMA model on it. Step 2, we first study the stationarity of the time series itself. We study it using the Dickey-Fuller test. In the case of non-stationary of this time series, we are looking for stationary differences. Most of the series will be stationary on the first differences, less often on the second differences. Also remember that the Dickey-Fuller test should be applied to the entire family of homogeneous indicators. And if you are not sure whether the family of your indicator is stationary or non-stationary, it is better to ask the teacher. That is, let's say you have the GDP per capita of France, and you will see that this GDP per capita of France is stationary. But what about others' GDP that are members of the family? Are they stationary or not? Here it is very important to analyze series that are stationary through the family and not just for the series itself. Because some exceptions with the same family may be, this is a perfectly acceptable thing. Step 3. Based on PACF, AKF, EAKF, we select 2 or 3 possible specifications for AR, AMA, and ARMA models. That is, in each of these models, we always have 2 or 3 alternative specifications. And each of these alternative specifications, in step 4, we test for autocorrelation of the residuals using ACF and the Lune-Box test. After that, we have enough reason to choose the final specification. This is the 5th step. That is, we must expertly decide which final specification of the model is best. And for this, we are guided by economy, that is the choice of a model with the smallest number of parameters. And secondly, the criteria for the absence of autocorrelation in the residuals. Here again, there is a choice that the researcher must make. Therefore, here you have to find this line, which of the model is better. You can feel it only in experience, in practice, when you build various models, see the results of forecasts from them, and understand what this or that criteria is worth in terms of savings or in choosing autocorrelation of the residuals. The 6th step is to build the forecast model of the final specification of the model. We will consider it in detail the forecasting techniques based on AR, AMA, and ARMA model in the next 3rd lecture. In fact, we will consider all the technical things there. But since the R package offers the forecast function, that is, the forecast is displayed by a simple command, then during the first seminar, you will already be able to build the forecast for the indicator, even if you do not fully understand how it is calculated. At the end of this lecture, I will say again that this algorithm for choosing the specification of a forecasting model does not take into account such important things that are observable in practice. Firstly, it is the presence of nonlinearity in the indicator, in particular structural breaks. We will have a separate lecture devoted to nonlinear models. That is, it is a drawback that this algorithm does not take into account nonlinearity. But in the next lecture, we will improve it and include nonlinearity in this analysis. And secondly, this analysis algorithm does not take into account the arch effect, heteroscedasticity, or square error correlation. This is also a really significant effect, but at this level, these simple AR, AMA, and ARMA models simply do not have time to include them. Again, we will consider this inclusion of the arch effect in our algorithm in our next lectures, and there will be already improved the result obtained. And again, looking ahead, let's say that taking into account the structural breaks and other way for taking into account nonlinearity, it quite strongly affects the forecast. But taking into account the arch effect rarely shifts the average forecast, but it greatly affects the risks assessment. That is, risk assessment is a spread of the time series. In risk management in financial markets, taking into account this arch effect is a very important thing, while the presence of a structural breaks is a significant thing to adjust the average expected forecast. But we will talk about all this later during our course. That's all for today. Thank you very much for your attention.